Hi guys, welcome to the video assignment for section 3.4. I'm going to go through this relatively quickly. I don't intend to spend an hour in the video. I'm sure you would appreciate that. So I am really just going to talk through the notes and maybe make some pointers. You, of course, as you watch this, if you need to pause or rewind or something, feel free to, of course, do that, and so that you can take your notes in the handout I gave you, or take the time to read through examples and so on. So I would recommend that you do that. All right, so otherwise, let's get started. Again, so in this section, we're going to talk about the inverse Laplace transform. So in section 3.3, you would have learned to find the Laplace transform. There is a definition with the improper integral that allows you to compute them, but probably even better, you have a Laplace transform table that we can look them up in. So for this section as well, you would also should have a Laplace transform table handy to refer to. I will also show you mine on screen as needed, but that's what we're going to look for. So in this section, we are looking to again, find the inverse Laplace transform of certain functions. Basically, the idea here is if you are given a certain function as a Laplace transform, what is the function that it came from? If you're given a big f of s, what is the function little f of t that you took the Laplace transform of in order to end up with big f of s? So again, we are inverting here. There is a little notation here. The notation here is I'm using capital L inverse to indicate inverse Laplace transform. Again, as we mentioned in the last section, most texts use a sort of scriptier, fancier L as their Laplace transform. I do not have access to one of those in my math palette, so I'm just using a capital L. Capital L inverse will represent a Laplace inverse. So I am told that there is, in fact, a definition and a general way for finding Laplace inverses. I have never actually seen that, but for our purposes and for practical matters, it is going to be much easier for us to simply try to use Laplace transform tables in reverse. So let's take a look at an example of some relatively easy ones. So for example, what is the Laplace inverse of s over s squared plus 49. So this one is a relatively easy one because this one is on the Laplace transform table, and we are just going to look at these in reverse. So my note here says this is number 8 on the Laplace transform table. So let me look up my Laplace transform table. If we look at number 8, which is down here. I can see it down here, yes. The s over s squared plus k squared is cosine kt. So let's go back to our packet here. So this guy here, well, the only thing we really need to realize is that, of course, 49 is 7 squared. So in the table, the k number is a 7. Hence, the inverse Laplace transform is cosine of 7t. So fairly easy. So again, this is the note here. This example was basically using number 8 on the Laplace transform table where k equals 7. The next one is also fairly straightforward, but we do need to look at it a bit more carefully. So we're looking for something on the Laplace transform table that looks something like this. So let's take a look. If I share my Laplace transform table, let's see what we have here. Let me get rid of those. This time, what we're looking at is something that looks like this guy. This is kind of what we have, yes? We have an s plus or minus a, in this case, an s minus a to the n plus 1 with an n factorial on top, this would be this as an inverse Laplace transform. So again, we're using the table in reverse. We're looking for something in the right-hand column and looking to rewrite it as the left hand. So I need to identify the A number and I need to identify the N number. So let's go back. We can take a look here. In this one here, I can see that we've got s minus 1 to the 3, so a equals 1 here, and then here we needed an n plus 1 here, so we read this as n 2 plus 1, therefore there should be a 2 factorial in the numerator. And the good news is that 2 is equal to 2 factorial, so this all works out. We basically have a number 17 where n equals 2 and a equals 1, so this would give us this. And again, so refer to your Laplace transform table. These are a little awkward and tricky at first, but if you see enough of them, it does become something you recognize a little more easily. Again, so these two are fairly straightforward. Now, a little bit of a helpful theorem here is linearity of the inverse Laplace transform. So this says the inverse Laplace transform of big F plus big G is inverse Laplace transform of big F plus the inverse Laplace transform of big G, and so on. So these three rules, this basically means, and it's basically the last one basically takes care of our cases here. This says if I want to take the Laplace inverse of an expression like this, I can go through and I can take Laplace inverses term by term, and constant coefficients can come outside the Laplace inverse. So this should all make sense because, as we saw in the last section, Laplace transforms are linear. It would be kind of weird, kind of hard to do if the Laplace transform were linear, but the inverse was not. So this requires, again, maybe factoring things out and so on. So a quick couple examples here. So there's a couple of my open math problems to try. So try the first one here. And again, you should have seen that the first one was fairly simple, doesn't take a lot of, if it matches up fairly directly to something in your table. Similarly with the second one, this is also a fairly simple one. Give that a go. Okay, so there's a couple of fairly easy ones. And I'd say they are easy in that they are relatively directly coming off the Laplace transform table. Now, a couple more examples, slightly more complicated. Find the following inverse Laplace transforms. What is the inverse Laplace transform of this function here? So the point here is that we can do this by linearity first and foremost, and that is we can break this up. We can do the Laplace inverse of 3 over s. We can then do minus the Laplace inverse of 2 over s cubed, and we can do plus the Laplace inverse of 1 over s plus 2. Again, when we break it up this way using linearity, then these are actually pretty easy. Each one of these is pretty easy and direct off the Laplace inverse table, relatively speaking. So give those a go, take a look at that, and then try one for yourselves here. All right, so moving ahead, slightly more complicated examples. So we're going to up the difficulty here in these next examples a little bit. The first one is really not too bad. What is the Laplace inverse of 10 over s plus 2 to the 4? So I would argue that this looks a lot like a number 17 again. So just really quickly, let's take a look at our table. Number 17 is this guy over here. Let me get rid of some of that again. So we have, in our example, we have an s plus a. That's fine. It just means that we should read. So we have an s. We have an s. We would read this as an s. Hold on one second. An s. Minus whatever our number was. I forget what that was. Let me just look that up real quick. So the question we're working on this was an s plus 2. So we would just read it as an s minus 2. So a is equal to minus 2. And then we have our exponent here. This is again a 3 for us. Therefore, n equals 2. Yes. So I want to look that up off the table. I can go back to my problem here and take a look. Yes. So in this one here, oh, and sorry, my mistake. This is a 4, not a 3. So this is now a 3 plus 1. Therefore, the n is 3 and the a is negative 2. That means if the n is 3, there's supposed to be a 3 factorial on top, not a 10. So I have a 10 in the numerator. It's supposed to be a 3 factorial. 3 factorial is equal to 6. So the way I fix this is by linearity. I can actually take the 10 outside the Laplace transform, the inverse Laplace transform. I can place a 6 in the numerator over here, or a 3 factorial in the numerator over here, and then balance it out by also dividing by 6. And I can divide on the inside, I can move it out and divide on the outside. So this is then the exact same function with the right factorial in the numerator here. So at that point, we can apply rule number 17 and get this guy. And then we can see that outside we have 10 over 6, which is equal to 5 over 3. So again, I just have to sort of manipulate it a little bit to make the form match up to my Laplace transform table. All right, here's another similar situation. How do we find the Laplace transform of this guy? Excuse me, the Laplace inverse of this guy, which is negative 2s plus 6 over s plus 4. When I look at this, these should become familiar to you. When you see this s squared plus 4 in the denominator, this should look like something familiar on our Laplace transform table. So let me erase that stuff here. Now let's see if we can find it. So basically, this is this guy over here, yes? We have basically in this problem, we're going to need these two things. We have an s over s squared plus a number squared, and we have a k over s squared plus k squared. These become respectively sine kt and cosine kt. So these are what we would be using here. So let's go back to the problem. So I need to, again, rearrange this a little bit to make this work out. I need to break this up into 2 terms. Notice that I can. I'm going to break this up into 2 terms. Negative 2s over s squared plus 2 squared and 6 over s squared plus 2 squared. Notice the negative 2 can be factored out. We can negative 2 can be factored out. So I can basically apply linearity. The negative 2 factored out, and in here, this is now directly a number 8. And then this guy here, this is a number 7. S squared plus 2 squared with a number on top. The number on top needs to be this k number here, which is the number 2. Now I have a 6, not a 2, but that's an easy fix. I can factor it, pull the 3 out in front, and now this is a number 7, and I can match it up. So basically I've got the number 2 in front, the number 2 in front, and then apply number 8 to get cosine 2t. And then for this one, I've got the number 3 in front, and then I can apply the number 7 rule to get sine of 2t, and there we have it. All right, so one more, and maybe the hardest one here, a little trickier, but let's work our way through it. For this one, we are looking at the Laplace inverse of 3s plus 7 over s squared plus 4s plus 8. So the first thing I'm looking at here, this is not going to be super obvious for you at first, but hopefully will become more obvious. When I'm looking at this denominator, I've really got 2 choices here. When I've got a expanded polynomial down here, the first thing I want to do is try and factor it. If it factors, great. We will talk about what to do if it factors in later examples. If it does not factor, it's because there's an irreducible quadratic factor like this one. If I have an irreducible quadratic factor, you just have to kind of take my word for it at this point. But the technique here is irreducible quadratic factor, you are going to complete the square, CTS for short. We're going to complete the square. So here's the work for completing the square. And when I'm done, my denominator looks like this. So s squared plus 4s plus 8 is equal to s plus 2 all squared plus 2 squared. So the reason we like this, the reason we're looking to do this is, once again, because if I look at my Laplace table, we have something that looks like this. So number 18 and 19. 18 and 19 have this s minus a squared plus k squared in the denominator. Yes, and that is what I have. I have something that looks like that. So these are what we're going to be applying. So these are going to end up looking like this: e to the at sine kt, e to the at cosine kt. So let's go back to the problem and see what we can do here. So again, I split this up. I'm going to do Laplace inverse. I'm going to do the 3s over this one first, and then we will do the 7 over this as well. So that is how I can split this up. So that is what I've done in the next line here. Yes. Notice then that for the first term here, I have an s in the numerator, and this matches up with that number in the Laplace transform. I believe that is a number 19 in the Laplace transform table with an s on the top. I just need to move the 3 out in front. For the other one, this is a number 18 in the Laplace transform table. I want to read that this 4 is, of course, a 2 squared. So the k number is 2. So I really want, oh, excuse me, scratch that. In the Laplace transform table, what we have in the numerator is, let me go back and share this again. I am getting myself confused with other Laplace inverse tables. In the number 19, in the numerator is an s minus a, and the number 18 in the numerator is just a k. So I have a bigger problem there than I initially thought. I have my 3 pulled out over here, and I have the s left in the numerator here. But my problem is that's supposed to be an s plus 2. So I am going to make it an s plus 2. I went ahead and added 2 here. If I add 2 here, you have to understand that what I've effectively done is added 3 times 2, which is a 6. So if I add a 2 here, I'm effectively adding 6 of these terms. And so to balance it out, I am subtracting 6 of them from over here. So that is a little, you might want to pause and take a minute to think about that step. There was a couple of examples of things like this, thinking this way, in the pre-class assignment that I had you work on. But the idea is, in order to get the plus 2 over here, I am effectively adding 6 because I would have to distribute by the 3. So to balance that out of this function, I am subtracting 6 on this other term over here. So if we look at that, then I now have a 3 times. This is now a number 19. And this one, this number is a 2. So I wanted a 2 up here instead of a 1. So I add a 2 up here, and I also divide by 2 out here. And again, linearity means I can pull the 3 out, I can pull the 1/2 out. The first one is now a number 19. The second one is now, actually, the first one is a number 19. Yes, I think the second one is a number 18. So this is what we get. So this is not obvious, I would suggest, how we get here. But again, this is your first hint. If it doesn't factor, if this doesn't factor, we complete the square, and we would have to do something like this. All right, so give that one a go. Give one on, there's an exercise like this in my Open Math, so give that a go. Okay, so let's now look at what happens if the denominator of this function does factor. So in the next example, we're looking at what is the Laplace inverse of s over s squared minus 6s plus 8. The idea here is this one factors fairly easily. You can double check me. This is what I get when I factor it. So that function that we're taking the Laplace transform looks like this. So the trick here is then to do a partial fraction decomposition. When you do a partial fraction decomposition, it's going to break down this expression into separate expressions that are much easier to find their Laplace inverse. So I have a little example of that, a simpler example of this. So take a look at this next example and give this a go. All right, so to continue then, we have to then perform a partial fraction decomposition. You should remember this from Calc 2. There's a little trick for this. I have written it up here. So the idea is we set up our partial fraction decomposition. In this particular example, we have a case number 1 partial fraction decomposition where we have 2 linear factors that are different from each other. In this case, the decomposition breaks up into one factor or one term of 1 over s minus 2 and another term 1 over s minus 4 like this. So the trick here is to take this denominator and clear out denominators, multiply on both sides by this lowest common denominator, and we get this. And then the trick is to understand that this expression here is an identity. It has to be true no matter what the value of s is. So we can pick convenient choices for s to make our lives easier to evaluate this. So one easy choice for s is to pick s equals 4. If I plug in s equals 4, I get the rather simple equation that 4 equals 2 times b. So b equals, let's see, 4 equals, I think I wrote that wrong in my notes there. This is 4, 2. So 4 equals b times 2. Therefore, b would be equal to 2, not a half. So this should be a 2, not a 1/2, my mistake. The other convenient choice for s is to pick s equals 2. If we choose s equals 2, we get a equals 1. That one I think is correct. So that breaks down the original question into this question, but these are much easier questions. Again, what were they? Number 7, number 8 type problems here. But again, this would now be a 2. This would be a 2. That was my mistake. So again, partial fraction decomposition allows us to break it down, our original problem, into components, into terms that are much easier, hopefully much easier to invert. All right, so give that a go, a partial fraction decomposition one here. All right, so here's just a little summary of partial fraction decomposition. I hope you will have seen this before. There are basically 4 cases of partial fraction decomposition. We just did a case like number 1, where the linear factor in the denominator is not repeated anywhere. These are all different. And then the thing you need to remember is what the setup is. So when you have different factors in the denominator, you basically make 3 terms like this, and you're trying to find the capital A, the capital B, and the capital C. If you have a repeated linear factor like this guy here, s minus a squared, then this is the setup that you have to perform in order to take care of that term. If there is another distinct term in there, you can make it another term on the end. So again, this isn't quite so much that every denominator is a case 1, 2, or 3. Every factor can be a case 1, 2, or 3. So basically, this one here, s minus a squared, was a case 2, and s minus b, I'm treating it like a case 1 because it's distinct and appearing by itself. There are also unfactorable quadratic factors possible in a denominator. So we can have things like this, s squared plus bs plus c, where this is not factorable any further. The setup, if you have a term like this, or a factor like this, the setup is to write it like this. So note the as plus b in the numerator. So that would be the idea. Number 4 is what happens if there is a repeated unfactorable unreducible quadratic factor. So you can see that here if you would like to, but I do not believe there will be any of those. Those get messy, and so generally those are not very common. I would probably say even number, well, I mean, 2 and 3 are not super common either. We'll see them here and there. So this is the setup, and then we can proceed with clearing the denominators and making our choices and what have you. So, all right, let's give it a go for some others here. The next one here is a little bit more interesting, i.e. a little bit more tricky. For this one here, we want the Laplace inverse of 12 over s squared minus 2s, s squared plus 2. And the first thing here, notice this actually factors a little bit further. I really want to read it like this. I've basically got 2 linear factors that are not repeated, and I've got an irreducible quadratic factor that is also not repeated. So the setup for this, according to that previous blurb above, is to set it up this way. This is how we would have to set it up. So this is the setup for the PFD here. We would then take this common denominator, multiply on both sides by this LCD to clear out all the denominators. And then once again, we know that this is an identity, and we can make clever choices of S to evaluate. So clever choices of S will involve picking S equals 0, because if I pick S equals 0, a lot of stuff goes away and makes the equation easier to solve. Another good choice is S equals 2. So always go for these first. The ones that when you plug them in, make a whole factor 0. So this whole factor would disappear, this whole factor would disappear, and we get a fairly easy equation to solve for B. Now, at that point in an example like this, I have run out of super convenient numbers to plug in to make the equation easy. So what I do then is I'm just going to pick the next easiest numbers I can think of that I haven't already used. So things like, in this case, I've already used 0. So let's use 1. If S equals 1, I can plug that in and come up with, in this case, I come up with an equation involving the 2 unknown coefficients, C and D. So we have an equation for C and D. So what I need to do is plug in another number. Again, the next easiest number I'm choosing to use is S equals minus 1. So if I plug in S equals minus 1, I basically got another equation for C and D. At that point, then we have a little system of equations for C and D. If you solve the little system of equations for C and D, we get a solution for C and D. We previously already found A and B. And so we can take those results and plug them in to our setup at the top here and get this result. So this is basically where we're at. Right, so now I can do linearity. So again, linearity, I can do these terms separately. The first two are actually pretty easy. So I went ahead and did those. Laplace inverse of -3 over s is -3. Laplace inverse of 1 over s minus 2 is e to the 2t. And then all I have to do is deal with this mess and invert this guy here. So this one here, what does this look like? This looks like sine and cosine again. Yes. So with sine and cosine, I'm looking for this s squared plus k squared in the denominator. For cosine, there is just an s in the numerator. So I can break this up into these two terms. This is the first one. And then this is the second one. The first one is heading for a cosine. The second one is heading for a sine, if I remember my Laplace transform tables well. So the first term, I can actually factor out that 13 over 2 here. And then this is my cosine. The other one I can pull out the 5/2 and get a 1 over s² plus the square root of 2. But the k number here is square root of 2. So I want a square root of 2 in the numerator. So I fix that here. I place a square root of 2 in the numerator. That means I have to also multiply by square root of 2 in the denominator to balance it out. And then this guy here is a number 7. So we have, again, the 13/2 is moved outside. This is a cosine root 2t. And then the other one is a 5/2 root 2 sine root 2t. So this one's a little bit more work, a little bit more of a challenge. So here's another one for you to try. This is the last example to try. This one is, again, it will be involving PFDs that are maybe not just case 1. So give that a go. Okay, last and perhaps least, here is one more example. This one's actually easier than the last one for a couple of reasons. Number one, the denominator has already been factored for us. And then number two, we basically have 1, 2, 3 distinct linear factors. So this is all a case 1 PFD. So I did the case 1 PFD over here, and this was an easier PFD than the last one was. I can compute my coefficients here. I found them all over here. I can plug them back in and then apply linearity. Yes, again, it's almost not worth writing the linearity, and I didn't here, and that the inverse of 1/3 over s is 1/3. The inverse of 1 over s minus 1 is e to the 1t. And the inverse of this one is the 4/3 comes out in front, and you have an e to the 6t. So this would be this guy. So that is that section on inverse Laplace transforms. We haven't really gotten into what Laplace transforms are good for, but suffice it to say that we are going to apply Laplace transforms to DEs. We are then going to be able to solve a DE inside of a Laplace transform, and then we're going to invert the answer to get back to our solution. So this is really quite clever and quite genius, really. If you are not seeing the point of these yet, that is probably fair, because we haven't really gotten to the point of these yet, but we will shortly after this section. But that's it for the video, and we will see you on the week when I get back. Thank you, guys. Bye.